Hi everyone, welcome back. Today we're going to be working on Chapter 11, and Chapter 11 is the goodness of fits and contingency tables. Now, we're mainly going to be focusing on Section 11.1, which is known as the goodness of fit. Now, we're going to start off with the definition of goodness of fit, and the goodness of fit is, as you can see here on screen, it's used to test the hypothesis that an observed frequency distribution fits or conforms to some claimed distribution. Now, this is going to be important for us, and to illustrate its importance, we'll go through and we'll look at this example that's listed right below. The example says that the M&M company claims that the distribution of plain M&M candies in a bag is 23% blue, 23% orange, 15% green, 12% red, 15% yellow, and 12% brown. So even though this is their claim, do you think this represents the true proportions of color distribution in all of the M&M bags? And if so, how would we check? Right? So this means that if we go to the store and if we buy an M&M candy bag, then we should naturally see proportion-wise 23% blue, 23% orange, 15% green, 12% red, 15% yellow, and 12% brown. Right? But at the same time, we're not going to go to the store and we're not going to buy, hundreds, maybe even thousands of these bags. Right? We want to make sure we develop a test, or we want to make sure we develop a mathematical or statistical method to be able to check this without having going to actually buy all of these products. Right? So what we then want to do is we then want to develop this baseline. What is the baseline that we're going to be looking at? Well, that baseline that we're looking at is this null hypothesis. This null hypothesis, we're going to say that the proportion, and remember, other synonyms that are synonymous with proportions is probability or percentages. So proportions, probabilities, percentages, this is all referencing the exact same value. So when we look at the null hypothesis, again, this is the baseline hypothesis, we're going to say the probability, or let me use a lowercase p for probability here. So probability that the color is going to be blue, this is going to be 23%. In other words, 0.23. The probability that we get orange is once again 0.23. The probability that we get green, and here's G, alright, probability that we get green is 15%. There we are. The probability that we get red, so I'm going to say probability red, and this is R, this is going to be 12%. Probability that we get yellow, that's a Y. Probability for yellows, this is going to be 15%, 0.15. And then lastly, we get probability of brown. Now, just be aware that we already used P and then B in this particular case. So what I'm going to do here is P sub BR, BR for brown, and this is going to be that we get 12%. So again, this is the baseline feature. This is what we're looking at. This is what we're trying to counter against. So, for the alternative hypotheses, what do we then want to see? Well, we just want to see, is any one or are any one of these probabilities any different than what's listed? Alright, so for the alternative hypotheses, we're going to say at least one of the listed probabilities is different. Now that means that, hey, when we start analyzing this, it could be that we get no browns in our bag. All right, that means that, hey, at this point in time, that probability is different, right? It'll automatically change all these probabilities too, but that's fine, right? So again, at least one of these probabilities is different is what we then want to see. So now we need to start developing this more mathematical method. How are we going to be developing this mathematical method to go ahead and test these hypotheses? Well, if we look down here, we're going to be looking at an expected count. All right, an expected count, this is how much we should be able to expect. Again, expected count, this should be more along the lines of that expected value that we were looking at. What should we expect to see if this was done a certain number of times? In other words, in theory, what should we be looking at? And then finally, we're going to have observed counts. What really happened? This column here is the column where we actually go out and actually buy these bags of M&Ms and then start annotating the percentages that we then see for the different colors. So again, expected is what we typically expect to see. What is that theoretical amount versus what is the actual amount? And then we're going to start calculating the differences to see how far we are actually off. All right, so we'll put a pin in that and we'll come back to it, and we're going to elaborate more on this expected count. So there are two ways of calculating an expected count. Number one, if the expected counts are equal, then E, in other words, the expected value that we're going to be looking at is just N divided by K. All right, and we'll explain what this N and K are. All right, so number two, if the expected counts are not equal, then we must use a calculation for the expected value. In other words, the average outcome is going to be N times P sub I. And this P sub I, this just stands for any individual probability that we have listed. So it doesn't mean that I is some random some probability that we don't know. It just means that I, as it states here, is the values that we are listing from 1 all the way to K. All right, so if we say P sub 1, that's the first probability. If we say P sub 2, that's the second probability. If we say P sub 3, then that's going to be the third probability, so on and so forth. All right, awesome. Now I did say I was going to come back and I was going to define what this expected value was at N divided by K. So N, this is always going to be that sample size that you're looking at. So I'm going to say sample total. Now K is going to be the number of categories. So N is a sample total, how much we're actually observing. This means that if I went to go buy the actual bags, then I'm going to be looking at the actual numbers for the total amounts of bags that I'm looking at. Versus the number of categories. Categories, I would then be splitting it into blue, orange, green, red, yellow, brown, so on and so forth. So we do see that there is these two different samples that we're looking at, or these two different numbers, and we must always observe, is it the total sample amount or is it the number of categories that we are looking at? Awesome. So now we can go through then and we can now start elaborating a little bit more as to how we're going to be running this hypothesis test. So down here we see this asterisk, and we're going to say that if the observation and experiment counts are close, in other words, they're going to be close enough, this means that when we run the expected counts versus the observed counts, this means that we are going to fail to reject. And we're going to fail to reject the null hypotheses. This is because if when we're looking at these observed counts, they're really, really close to these expected counts, then that means, hey, your null hypotheses could possibly be true. And in that sense, we cannot fail to reject. Number 2, second asterisk. If the observation and experiment counts are far apart, in other words, there's going to be a big difference between what we observed and what we expected, that means that there is some type of discrepancy, and we then must reject the null hypotheses. This means that looking at this original hypothesis, the claim from the M&M company would actually be rejected at this point in time, because we have enough sample evidence to then support our alternative hypotheses. Awesome. So let's go ahead and let's start jumping into this. So in here, what I want to do on this first example, it says that finding the expected counts. All right, so we now have to go through and find the expected counts. Part A. A single die is rolled 45 times with the following results. Okay, so before I go on, I'm going to look at my table here. Alright, so looking at my table, I should have 45 of these counts. So again, I'm going to start analyzing. N is my sample amount. Well, what is that sample amount? That is 45 times. Alright, categories. In this particular case, we have categories that we are splitting all of these samples into. How many categories are there? Well, there are 6 categories. Alright, so this part up here, these are the categories. Alright, we had 1, 2, 3, 4, 5, 6 of these categories. Awesome. So these 45 numbers were split into these 6 categories. Now, I'll go back and I'll elaborate what that means in just a little bit. So before we carry on, let's go back and let's actually finish the sentence, or the introduction here. Assuming that the die is fair and all outcomes are equally likely, find the expected frequency E for each empty cell. Alright, so here goes our job now. Alright, so we again want to find that expected frequency for each empty cell. So again, we're looking at the observed. This is what we actually ran through the experiment, or somebody actually ran through that experiment. We now want to see, okay, if we were going to roll these if we were going to roll this die 45 times, how many ones would we expect to appear? Well, in order to do this, right, all the expected counts are equal here. This means that the chance of rolling a 1 is the same chance as rolling a 2, is the same probability as rolling a 3, same probability as rolling a 4, a 5, or a 6. Which means, in this particular case, our expected counts are all going to be n divided by k. In other words, 45 divided by 6. Because again, we have 6 categories. Every single category is equally likely to happen, and therefore these 45 times are going to be split into these 6 categories. Mathematically speaking, we're going to divide 45 by 6. So let's go to the calculator, get that calculation, and then we'll annotate what we get. Alright, here we are. So once again, we're going to do 45 divided by 6. Enter. We get 7.5. So we should expect 7.5 for each individual category. That is the outcome that we are observing. That is the outcome we are expecting. Let's go back and let's write it down. All right, here we are. So let's go through. Now, the first expected count was 75. 7.5. Second expected count was again 7.5. Again 7.5 for the third, for the fourth, for the fifth, and for the sixth. And again, this is because all of these values, all of these categories are equally likely. Since they're all equally likely, then we must naturally get 7.5 every single time. So the number 1 is going to appear 7.5 times, number 2 7.5 times, so on and so forth. All right, we're not going to worry about the decimals happening here, because at the end of the day, we're going to be using this data for the probabilities that we're going to need to observe. And within those probabilities, we want to make sure that all of this data is not approximated, because the more we approximate, the more error that we introduce into our calculations. So let's not go through and let's not round yet. Okay, now let's look at part B. Part B says that John works as an usher at a theater. The theater has 1,000 seats that are accessed through 5 entrances. All right, so we have a theater, and we're going to have these 5 entrances. All right, so we got to kind of keep that in mind. Each guest should use the entrance that's marked on their ticket. Entrances A and B should receive 30% of the guests using these entrances. Entrance C should have 20% of the guests using it. Entrances D and E should have about 10% of the guests using these entrances. So what we want to do is we want to find the expected frequency for each of these entrances. Now, again, this is now going to be more of a realistic outcome here, right? Because if you're running a theater and you wanted to start on time, the gates or the doors typically don't open till a certain time. And what you want to do is you want to start funneling people through these gates or these entrances in a very timely manner, not only so they can find their seats or they can find their spots, but so that they can then peruse the venue, buy certain things, souvenirs, anything that you want them to, so that they can buy and stay inside of that theater. So you want to get them in there as fast as possible. This means that we're going to have to split our entrances to receive a certain amount of percentage of guests. Now, you might see this occurring in a baseball park or in some type of venue that has all these different entrances. And these parkings or these gates are made to funnel people through that are expecting higher volume on one side of the venue versus the other. So, let's start dissecting this. 1,000 seats. So the theater at this point in time has 1,000 seats. That is the sample size that we're looking at, because there's going to be 1,000 people coming through to fill in these seats. Okay, how many categories? Well, I have category A, B, C, D, and E. That means I have 5 categories. So in here, my K value is 5. Awesome. Now, we're going to go through and we're going to start identifying the probability. All right. Notice that each category does not have the same probability outcome. Entrances A and B should have 30%, so those two are the same, but entrance C should have 20%, and then D and E should both have 10%. So again, naturally, we have different percentages or different probabilities, which means we're going to use the second part of the expected outcome. So out of this 1,000, out of the 1,000 amount, how many should we expect to use gate A? Well, gate A corresponds to 30%, which means 30% of 30% of 1,000. So this is just 1,000 multiplied by 0.30. So what's 30% of 1,000? That's 300. Next one. Category B, or entrance B. Well, entrance B, once again, we have 1,000 we have 1,000 ticket users coming through, and they're going to be going through gate B. Gate B, once again, has 30%. Which means how many people, how many ticket holders should we expect to be going through gate B? 300. Let's look at gate C. Gate C, once again, we have 1,000 people here. So 1,000. Oops, you know what? Let's use it here. So we have 1,000. Now, gate C, according to the work that we have here, let's do this in a different color now. Let's go with this one here. So gate C, where's gate C? Here we are. Gate C should have 20% of the guests, which means we're going to multiply by 20%. This means it's going to be 1,000 multiplied by 0.20. So naturally, 1,000 times 0.20, or 20% of 1,000, that's just 200. So 200 people we should expect to be using gate C. Gate D, now is where we look at that last part. So gates D and E is all 10%. So what is 10% of 1,000? Well, some of you can do this in your head, and that's perfectly fine. If you cannot, then that's okay. And just multiply 10% by 1,000. Or in other words, 1,000 multiplied by 0.10. So we should now expect 300 guests are going to be using gate A, 300 guests are going to be using gate B, 200 guests are going to be using gate C, 100 guests are going to be using gate D, and another 100 guests are going to be using gate E. And that's all there is so far for this goodness of fit. Now that we've developed a method to start observing these observed counts and these expected counts, and how to identify the expected counts a little bit more clearly, we now want to actually dive a little bit more into how we're going to set up this hypothesis test. So again, what we want to do is we want to do what we were doing in the last page. Find the expected counts, all right, and then number of categories. So find your K value and then look at your expected counts. Check the requirements. Is the data randomly selected? The sample data must consist of frequency counts for each of the different categories, and then for each category, the expected frequency is at least 5. Now, I want you to pay special attention to these hypotheses here. So I'm actually going to highlight these hypotheses in red here, because these are very, very, very important for what we're doing. Let me actually increase the font size here. All right, there we are. So these are very, very important simply because we are now going to be running one of two hypotheses. Notice the null hypotheses, number one scenario, all outcomes are equally likely. If you go back to the first page, that was one of the expected outcomes or expected counts, that they were all the same. So if they're all the same, then that means each probability listed must be the same. The alternative hypothesis is that at least one of these probabilities is different from the others. Okay, nice. Second outcome, null hypotheses. We're going to be given individual probabilities, kind of like how this one is here. Probability of blue, that was 0.23, probability of green, 0.15, probability of brown, 0.12. So these are the ones that are different probabilities. And the alternative then says at least one of the probabilities is different from the claimed distribution. So the way I worded it here is that at least one of these listed probabilities, and that's the ones that we listed here, is different. So again, we have to make sure that we pay attention to the verbiage and we use the proper verbiage for the respective hypothesis test. Now, level of significance, we're just going to be using alpha. The test statistic that we are looking at. So this is your test statistic here, and this test statistic is known as your chi-square. This is a Greek letter for chi, and again, it's not chi, but it is chi-square, because again, we have the chi letter here, and we're squaring it. So again, chi-square. This chi-square distribution is always going to be a right-tailed test. Now, if you were following along with the previous section when we were determining correlation and regression, anytime that we did a hypothesis test, was always a two-tailed test. So that was always nice to see. In this particular case, the chi-square distribution is always going to be a right-tailed test. So always keep that in our back pocket. Now, what does this mean then? Well, what this means is that when we take the summation, or when we add all of the square differences between the observed and the expected counts divided by the expected counts, this should get us this chi-square. So what I'm going to say here is that O, this is your observed count. E is your expected count. All right, so we have this observed and we have this expected, and that's exactly what we want to see. All right, awesome. Now, we can use either the critical value method or the p-value method to double check or to ensure that we are either going to reject the null hypotheses or we're going to fail to reject. And the same process is going to occur if it falls within that shaded region. Remember, I call that the friend zone. Anytime it falls in the friend zone, we get rejected. That means the null hypothesis must be rejected if it's in the friend zone. If it's not in that friend zone, then we must fail to reject. Regardless of what method we're using, either the critical value or either the p-value method, we're still going to arrive at the exact same conclusion. Another item that we want to focus on here is these degrees of freedom. Notice the degrees of freedom are no longer based on the sample size. Now the degrees of freedom are now based on the categories. So how many categories do we have? We have to find out. Categories, like in the die example here where they rolled the die 45 times, there were 6 categories. Therefore, the degrees of freedom is just 6 minus 1. In the example here for the theater, there was 5 categories, so my degrees of freedom there for that example would just be 5 minus 1, which in turn would just be 4. Alright, so not too bad. And again, we're still going to go through this exact same process, and we're going to start extracting all of these values. So on here, you're going to see that your TI-84 actually does a goodness of fit test. We're not going to use it right away, but instead we're going to save that, and we're going to do all of this manually first, and then we're going to come back and revisit that topic in using that calculator. So let's go ahead and let's start on this example then. So please take some time, read the example, and then we'll go through and we'll find what it is that we'll need and what we need to extract, and then how we're going to do some of these calculations. Alright, so the M&M company claims that the distribution of plain M&M candies in a bag is 23% blue, 23% orange, 15% green, 12% red, 15% yellow, 12% brown. Very similar to that example that we had. Suppose we took a simple random sample. Alright, so that's super important here. Super random sample, nice, of 400 M&Ms. So far what I have annotated here is that the sample is for 400 M&Ms from the population of all M&M candies the results are shown below. We have blues, orange, greens, red, yellows, and browns. Okay, that's kind of nice. Now, what does that mean for us category-wise? Well, category-wise, that means we're going to have 6 categories. One of them blue, orange, green, red, yellow, brown, so on and so forth. Now, these probabilities are all different. So that's one of the items that I then start looking at, is the probabilities are different. So I'm going to denote here that each probability is different, and I'm going to denote it somewhere here. So I'm just going to say each probability is different. Now, because each probability is different, I then need to calculate what is the expected amount that we're going to be looking at for the blues, for the oranges, for the greens, so on and so forth. So let's start with those calculations then. So to find the expected counts, I'm just going to label this row E, and then this row for the frequency amount, I'm going to observe as my observed count. So the frequency is the observed count. All right, that's awesome. Expected, how many did we expect? All right, so to find this expected, I'm going to use N, in other words, how many of the sample are we looking at, times P sub I. And remember, P sub I is just the corresponding probability to that category. So when we have blues, so how many did we expect to be blue? Well, if we take 400 and multiply it by its respective probability for blue, that means we're looking at 23% of them being blue. There we are. So all we do is go to the calculator and figure that out. Here we are. So again, 400 multiplied by 23%, or in other words, 0.23. Oops, no, just 0.23. There we go. And we get 92. So we expect to see 92 blues if we go out and observe 400 of these M&M samples. So let's go back. Here we are. All right, so again, we should expect to see 92 blues. Orange. How many orange M&Ms should we expect to see? Well, again, we're going to take the 400. Out of the 400 that we're observing, what's the probability for orange? Well, the probability for orange is given to us right up here. So that's 23%. So again, 0.23. Once again, that should be 92. So again, we should expect to see 92 of these orange candies that we're going to be looking for. Green. Okay, again, out of the 400. So out of the 400, how many do we expect to be green? Well, percentage-wise, that's 15%. So all we do is take 15% of 400, and we should expect to see 60 of them. All right, I want you to fill in the rest of the table then. With their respective probabilities, find out how much of those 400 should we expect to see. Please fill it in now. All right, so these are the values that you should have gotten. That for the expected count for the reds, we had 48. The expected counts for the yellow, we had 60. And the expected counts for the brown, we had 48 once again. So the question then becomes, is the proportion of each color different than the claim of the M&M's manufacturer? All right, so now we have to go through the hypothesis testing. So what I want to do first, excuse me, is identify the null hypotheses and the alternative hypotheses. So let's go through. For the null hypotheses, well, the null hypotheses, I'm going to say that I have a probability that a blue color or a blue colored M&M will be 23%. All right, so 23% for the blue. We have that probability for the orange. So probability for orange should be 23%. Oops. There we are. Probability for the green should be 15%. Probability for red should be 12%. Probability for yellow, 15%. And finally, probability for brown should be 12%. Now, my alternative hypotheses. I want to then list, since these are not equal, then the probability is not going to differ from them, but it's going to differ if at least one of them is different. So my alternative hypothesis here is that at least one of the listed probabilities is different. Awesome. Perfect. So what we're going to do now is we're going to find this test statistic. Now, the test statistic is actually given here, right in here. This is a test statistic that we're going to be using. All right. So what we need to do is we need to find the difference between each expected and each observed count, and we need to divide it by the expected count. So when we look at our test statistic, I'm just going to write the formula right in here. So that's going to be my chi-square. And again, this is going to be my test statistic, so I'm going to put a little star here. This is going to be the summation of the observed minus the expected squared divided by the expected. So let's go through and let's start identifying this. Chi-square. Here we go. We're going to go through the first count. All right, so let's go through the first count. What was the observed count? So the observed was 80. So this becomes 80 minus, what was the expected? 92. So 80 minus 92, we're going to square this, and then we're going to divide this by the expected amount, which was 92. There we are. Plus, second column. All right, what was the observed? Well, the observed for the second column was 75. So that's 75 minus 92. Square that, divided by 92. So here we have column 1, then we have column 2. Now I need to go to column 3. Column 3, expected minus observed. That's 48 minus 60 squared divided by 60. All right, third column done. Fourth column, 66 minus 48, square it, divided by expected count, which was 48. Next column, we're going to get 72 minus 60 squared divided by 60, the expected amount, plus the final column. So the final column here is going to be 59 minus 48, square this result, divided by 48. There we are. Looks pretty good. All we have to do now is insert all of this into the calculator. So let's go through and let's start inputting all of this into that calculator. So follow me along to the TI-84. Here we are. I'm going to clear this. Alright, so here goes the first one. I need a fraction, so what I'm going to do is I'm going to do my typical alpha, then the y equal to, and I'm going to select number 1 because that accesses my fraction. I'm going to put a parenthesis up here, and it's going to be 80 minus 92. Close that parenthesis, and then square that amount. Alright, so 80 minus 92, quantity squared. I'm going to use the down arrow to go down below, and I'm going to plug in 92. Use the right arrow. There we are. Insert a plus, and do this all over again. Alpha, y equal to, enter. I have a fraction, parenthesis. That's going to be, what is that, 75 minus 92. So 75 minus 92, square that amount, divided by 92. Once again, I'm going to go through the addition for the next one. That's y equals 2, there we are, and we're going to keep going. Alright, so 48, oops, excuse me there. 48 minus 60, quantity squared, divided by 60, plus, once again, same thing. Alright, 66, oops, cheese and crackers, 66 minus 48, quantity squared, there we are, divided by 48, looking good, plus, once again, fraction, there we are. The next one's going to be 72 minus 60, quantity squared, scroll down, divided by 60, oops, divided by 60, there we go, enter the plus, one more fraction, there we are, up top, so that's going to be 59, so 59 minus 48, square that, divided by 48. Perfect. So once we have all this set in, all I have to do is just hit enter. And I get this fraction. Notice that when I get the fraction, you might say, oh, hey, Mr. Castor, I got this one fraction and my calculator's not converting it into decimal. It's okay. It's okay. What I want you to do then, if you get this fraction number given to you, what you're going to do directly now is you're going to press math. You're going to scroll over to number. So scroll to the right. There we go. Or actually, sorry, we want math. My apologies. We want math, and what we want to search through, or what we want to convert it to, is the decimal. So I'm going to go down to number 2 here. There we go. So what the calculator is now doing is it's taking this fraction answer, the fraction answer, and it's going to convert it into a decimal. Press enter. There we go. Look at that. Isn't that beautiful? So we get our test statistic. This chi-square is 18.777. Let's go back and let's write that down. Here we are. So we get 18.777 as our test statistic. All right, perfect. So what we get to do now is we get to either use the critical value region or we get to use the p-value method, one or the other. So let's go through and let's start identifying what it is that we're going to be using. Whichever one we want to use, we'll then go through and we'll use that amount. Or sorry, we'll use that method. Alright, so let's go ahead and let's decide p-value or critical value method. Now again, doesn't matter which method we use because they're all going to lead us to the exact same conclusion. So I could use the critical value method here, alright, and that'll be fine. So if I have my test statistic, I now need my critical value then. So in order for me to get my critical value, alright, and again, I'm going to say here that I'm going to be using my critical value method. Alright, so for the critical value method, I already have my test statistics, so all I need is a critical value, which means I need to use all of the information that I have. So what I'm going to need to do here is I'm going to need to find my degrees of freedom. So degrees of freedom, if you remember, the degrees of freedom is going to be this k minus 1, which k is 6 categories, so that's going to be 6 minus 1, which is going to be 5, and I need to find my significant level. Well, level of significance, if no level of significance is given, then naturally we will always default to 0.05. So this means that we now need to extract what is this critical value that we're looking at. So I'm going to say here, find the critical value from table A4. Alright, so let's go look at table A4 really quickly, that way we can find that critical value. Alright, so here's the formula card that you all have access to on Canvas. Alright, we've seen this before when we were doing the correlation. Alright, when we're doing correlation we use table A5, but now we're going to table A4. So we're going to scroll down table A4, not this one, and not that one. Here we go, table A4. Notice it says chi-square distribution, so we're already in the right table. Degrees of freedom. What's the degrees of freedom that we're looking at? Well, we're looking at degrees of freedom of 5. All right, so that's cool. So degrees of freedom 5, and what's going to be the area to the right? Well, we're using area to the right as 0.05, so that's going to be this one here. So let's go degrees of freedom 5, and we're going to 0.05 for the area to the right, which means the critical value that we need is 11.071. This is a critical value that we need. Let's go ahead and let's take that back to our paper. All right, here we are. So the critical value that we found, the critical value from here, was that we get that our chi-square is going to be 11.071. Again, this is the critical value. So I'm going to find my critical value, all right, somewhere here. And this critical value is going to be 11.071. Oops. This is my critical value. Test statistic. All right, so this is my shaded region now. Test statistic is the one that we're going to be looking at here. Where does 18.77 fall in? Well, 18.77 falls somewhere in here. 18.77. This is our test statistic. The test statistic falls within the shaded region, so what do? We reject the null hypotheses. All right, so what if we don't want to use the critical value method? What if we then want to use a p-value method? So the p-value method. All right, not too bad. So if we're going to use the p-value method, we need the p-value and we also need the alpha. Alpha is not too bad. Alpha is already given to us, or alpha we extracted as 0.05. So let's try to find then what is that p-value. So for the p-value method, in order to extract the p-value, we're going to use a chi-square distribution, and in here we're going to use chi-CDF in order to extract this. And what I'm going to do here is we need to insert a lower bound and an upper bound. So lower bound here is going to be this one here, which is 18.77. Upper bound, remember we just need some large upper bound, so 1E99, and we need the degrees of freedom. Degrees of freedom here is going to be 5. All right, so let's go to the calculator and let's start actually observing this. So let's go through on the TI-84. Follow me along. All right, here we are. So I'm going to go to TCDF. So I want that distribution, so I'm going to press second distribution. There we are. Notice I'm going to go down here to chi-square CDF. That's number 8 on that distribution, chi-square CDF. Notice lower bound 18.777. That's what we were just discussing. Upper bound 1E99, degrees of freedom 5. Paste this, and it says chi-square CDF 18.77, comma 1E99, comma 5, exactly as I had it written down. You press enter, and there you get your p-value. That is your probability associated with that test statistic. Let's go back and let's write that down. All right, so again, I'm just going to modify this really quickly. Chi-square CDF, there we go. So we get the p-value to be 0.00211. And again, what do we compare the p-value to? Well, we always compare the p-value to the alpha level. So we're going to compare this to 0.05, and this is our alpha level. Which one is larger or which one is smaller? So naturally the p-value here is smaller. If the p is low, the null must go. Therefore, we reject. So using the p-value method, I showed my work here and I was able to find that we're still going to reject. Critical value method, still the same work that went into it, and I'm still going to reject the null hypotheses. Conclusion. There is enough sample evidence to warrant the rejection of the claim that the proportion of each color of M&Ms follows the claimed distribution. And I'm going to finally say at alpha is equal to 0.05. So again, we're using the alpha as 0.05, and again, what I'm doing here for the conclusion is I'm summarizing. Based on the sample evidence, what do? Well, we want to reject. And what are we rejecting? Well, we verbalize the null hypotheses, right? So we're going to reject the null hypotheses, and the null hypothesis says that we are claiming that the distribution, or that the proportion of each color of M&M follows that distribution that we listed up above right here. So again, verbalizing everything that we have for our conclusion is what I'm looking for. Nice. So that's problem number 1. Let's go to problem number 2. A company sells their products exclusively by mail. The company's management wants to find out if the number of orders received at the company's office on each of the 5 days of the week is the same. The company took a random sample of 400 orders received during a 4-week period. The following table lists the frequency distribution for these orders by the day of the week. So again, they're now looking at Monday, Tuesday, Wednesday, Thursday, Friday. Each individual work period, all right? Not bad. The number of orders, we have 92 that arrived on Monday, 71 that arrived on Tuesday, 65 Wednesday, 83 Thursday, and 89 on Friday. Okay, not bad. So now what we're then going to do is we're then going to start looking at what is the expected. So again, number of orders here, this means that the first column, that is the observed amount. All right, so the observed amount was this. Expected, how many did we then expect to occur? All right, so let's start analyzing, or let's start extracting. How many samples did we look at, or did they look at? 400. How many categories? Well, 400 because of the 400 packages. Well, category-wise, we're looking at 5 different categories. K is equal to 5. Now, we want, at this point in time, notice that the probabilities are not listed for each day of the week. So what we're then going to do is we're going to assume that each probability or each day of the week has an equal chance of getting the same amount of packages. Which means, how many packages should arrive on Monday, how many packages should arrive on Tuesday, Wednesday, Thursday, Friday, so on and so forth. So the probability that we're going to be looking at here is always going to stay the same. So we're going to use n divided by k. All right, so here we go. In this particular case, n divided by k is what we're going to be looking at. What's n divided by k? Well, we have to do what's 400 divided by 5. All right, so let's go ahead and let's figure that out. 400 divided by 5, and you guessed it, just 80. So this gets us 80. So we expect 80 packages every single day. Monday, Tuesday, Wednesday, Thursday, and Friday. All right, not too bad. So now we're going to test the claim that the orders are evenly distributed, and again, that claim is part of why we did this 400 divided by 5, evenly distributed over the 5 days of the week at a significant level of 0.025. So let's go with the null and let's go with the alternative. null hypotheses. We're going to claim that the probability for Monday is the same as a probability for Tuesday, is the same as a probability for Wednesday, same as a probability for Thursday, and same as a probability for Friday. All of these probabilities are the exact same. So the probability 1 day out of the work week, so 1 day out of 5. So probability here is 1 out of 5. 1 day out of the 5, this should be 0.20. So again, the way you find that is 1 divided by 5 on your calculator, and you should just get 0.20. There we are. Alternative hypotheses. What we're going to say now is at least one of the day's orders is different. All right. So at least one of them is going to be different. So let's go through and let's identify what is going to be our test statistic. So test statistic here, we're going to use the chi-square. So chi-square test statistic, here we go. We're going to go to the first column. First column, we're going to do O, which is 92. That's the observed minus the expected divided by expected. Second column. Second column is 71, that was the observed, minus the expected, which was 80, square it, divided by the expected, which was 80. Next column, 65 minus 80 squared, divided by 80. And we keep on repeating this process for the rest of the columns. Next one is 83 minus 80, quantity squared, divided by 80. Next one is 89 minus 80 squared divided by 80. Now we need to input this into the calculator. So let's go to the TI and let's go ahead and start inputting this in. Here we are. So I cleared everything on my calculator. I'm going to go through and I'm going to start inserting these as fractions. So the way that we insert fractions is the same way that I've been showing you this whole time. So do a fraction. There we go. Open parenthesis for the numerator, so open parenthesis, then it's 92 minus 80 squared divided by 80, looking good, plus, there we go. Next one is going to be 71 minus 80, square that, divided by 80, plus, fraction once again. Numerator is going to be 65 minus 80 squared divided by 80. Next one, parenthesis here, it's going to be 83 minus 80. Oops, I didn't put the 80 there. 83 minus 80, there we go, squared divided by 80 plus fraction once again, and I believe this is going to be the last fraction, which is going to be 89 minus 80 for my numerator. So 89 minus 80, there we are, square that, divided by 80. Once you get everything in here, all you need to do is press enter, and there we are, 27 over 4. Again, if you get a fraction, try not to worry about it. We're going to go to math right in here. So math, then we want the fraction and we want to convert it into decimal. So that's the number 2 option. Just press enter. Answer converted to decimal, 6.75. Awesome. So let's take that 6.75 and let's write it down on our paper. Here we go. So chi-square test statistic, we now got this to be 6.75. Awesome. So now there's 2 ways that we can do this. We can now proceed using either the p-value or the critical value method. Again, I like using the critical value method or the critical region method. Critical value method. That means I'm going to need a few things. I need my degrees of freedom. So degrees of freedom is k minus 1. K is 5, so 5 minus 1 gets us 4. I need my alpha level. Alpha, they actually give us our alpha as 0.025. Nice. So what I'm going to do at this point in time, using this critical value method, I then need to extract what is the critical value that I'm looking at. In order to do that, I need table A5. So let's go to table A5 along with our critical value, along with our degrees of freedom and our significance level. All right, here's table A5. So, table A4. My apologies. Table A4. Degrees of freedom. Remember, degrees of freedom is now 4. Area to the right. Area to the right is our significance level that we're looking at, which is 0.025. So 0.025 and degrees of freedom of 4. So I'm going to go degrees of freedom of 4, and here we are. Area to the right is 0.025. That means my critical value is 11. Here we go. Is 11.143. So let's go back and write that down. 11.143. So 11.143. And again, this was found by using table A4. Awesome. So we found this critical value, and that critical value says that it must be 11.143. So 11.143, 11.143, right in here. Anything to the right in that shaded region, we're going to reject. Our test statistic falls at 6.75, right in here. It does not fall within the shaded region, so what do? We fail to reject the null hypotheses. It's not enough information at this point in time. All right, so again, that was the critical value method. What if we do this using the p-value method? So the p-value method. So for the p-value method, I'm going to extract my p-value, which means I need my chi-square distribution. So this is going to be chi-square CDF. I'm going to need a lower bound. So the lower bound is going to be the 6.75, 6.75. Upper bound, I just need some random upper bound. So let's make this a really large upper bound, 1E99. And degrees of freedom, which is going to be 4. So follow me along to the calculator, and we'll go ahead and we'll start extracting what is this p-value that we're going to need. Here we are. So again, I want that distribution. So second distribution, go over down to chi-square CDF. Chi-square CDF, we're going to insert what we found, that's 6.75. Upper bound, since this is always a right tail test, it's always going to be some large upper bound. Degrees of freedom was 4 in our case. Again, it looks exactly like I wrote it down on the paper. Press enter, and we get this p-value to be 0.1497. Let's go ahead and let's write that down. All right, here we are. So my p-value, what I extracted here was 0.1497. All right, and again, we always want to compare that to our alpha level. Alpha, which was given to us, is 0.025. All right, now, which one is larger? Which one is smaller? In this case, the p-value is larger, which means if the p-value is large, we must fail to reject the null hypotheses. Whichever method we use, critical value or p-value, it will always lead us to the exact same conclusion. So, what is that conclusion? Well, the conclusion here is going to be that, let's scroll, here we go. There is not, sufficient, I just realized I'm doing this in black, not blue, there we go. There is not sufficient sample evidence to warrant rejection of the claim that the orders are evenly distributed over the 5 days of the week. At significance level of 0.025. Now, again, all we're doing here is we're just summarizing, hey, what we found is we cannot reject the null hypothesis. And why can we not reject it? Well, there's not enough sample evidence. So there's not enough sample evidence to warrant the rejection. So again, to sustain that rejection of the claim. And what was that claim? That claim was that we were looking at all of the probabilities being exactly the same. All right. So there is not sufficient sample evidence to warrant the rejection of the claim that the orders are evenly distributed over the 5 days of the week. And that's all there is to it. All right, so I hope you all enjoyed this lesson. This was section 11.1. Next time we're going to cover section 12.1, which will be ANOVA testing. So that is the last section that we get to cover in this course. So I know with everything going on, there's a lot of stress, a lot of turmoil going on. So if you have any issues, any problems, again, please feel free to contact me regarding these issues and how they're affecting you, and we'll take it from there. All right, so I hope you all are staying safe and be careful, and I hope to see you all next time.